So why is diagonalization important? Because we don't like doing matrix math. And by what I mean by that is like powers. So like 8 to the 17th is not very easily like computable, but when you do like your diagonal like decomposition, um, then that's the whole like point of it as like a background. So as I'm sure you guys are very familiar with by now, A equals C D C inverse, where D is the diagonalized eigenvalues, and C is the corresponding eigenvectors. Okay, so we have D equals, let's have a 3 by 3, we'll say lambda 1, lambda 2, and lambda 3, with the zeros everywhere else. That's what that big 0 means. And we have C equals vector, eigenvector 1, eigenvector 2, eigenvector 3. Okay, totally corresponding to whatever column that these are in. Okay. And you find these by, we're going to go through like the character's polynomial, how to find eigenvalues, eigenvectors, everything across that line. So how can you tell if something's diagonalizable? You have to find your eigenvectors. Okay. So the way that something is diagonalizable is that it has like for an n by n matrix, it is diagonalizable if you have n linearly independent eigenvectors. Another way to say this, the sum of geometric multiplicities equals n. That's just another like qualification you can think of it as. Like if you have like one repeated eigenvalue, lambda equals 2, lambda 1 and lambda 2, and you only get a vector 1 equals something like this, then you cannot have a diagonal matrix because for every eigenvalue here, there is not an eigenvector. Like you would have a 2 here, and then you'd have that vector down here, and then you'd have another 2 here, and you can't repeat the same vector there. So that's why that doesn't work. I know the writing over isn't very clear, so I'll just write that over here as well. So in this case, we have something that looks like this for our D, and for our C, we would have our V1, but we don't have a V2, so nothing can go there. So it's not diagonalizable. That's the whole idea. If we had like a V2 equals 0, 1, then sure. That would replace that, and it would become diagonalizable. Geometric multiplicity is how many times like you have that 0 in your character's polynomial when that's equal to 0. Geometric multiplicity is how many eigenvectors you get from that eigenvalue. Okay. So let me see if I can pull an example from one of the midterms to go over this, or one of the practice midterms. Any questions about this stuff while we're looking at it right now?
Why isn't it working?
So
Mhm.
you were right there is saying the n by n matrix is diagonalizable if n is less than I. Or,
No, that's a linearly independent.
oh, okay, sorry.
No, that's fine. Linearly independent.
Oh, okay. The columns or
It's square, so n is columns and rows.
okay.
That's the whole like nice part about what we're doing. Well, part of it at least.
So you can have eigenvalues that repeat, but not eigenvectors that repeat, and it would still be diagonalizable.
You can have eigenvalues that repeat. Yes. You can have eigenvectors that repeat. No. Yeah. Does anybody have an example of one of these in one of the midterms? I'm just scanning through like the practice midterm to see if there's a question that asks if it's diagonalizable.
Question 13 might be a good example.
13. Yeah, that is a fantastic example.
Sorry, but
Mhm.
are you saying that the eigenvectors, if n has n linear independent eigenvectors, or are the columns linear independent, or the rows, for it to
If
be diagonalizable?
Okay, so if you have n linearly independent eigenvectors, it is diagonalizable.
Okay.
And the statement, this is another really important statement to know, for like C distinct eigenvalues means you have at least C eigenvectors. Lambda is technically not the term to like use, but I'm just calling that in terms of eigenvalue.
Okay.
This is really important. So if you have like a repeated 2, like if you have like in this case we had an algebraic multiplicity of 2, right? So we have one distinct eigenvalue, which is 2. So we have at least one distinct eigenvector. If we had like a lambda equals 2 and a lambda equals 3, then we have two distinct eigenvalues, and that means we have at least two distinct eigenvectors, and then you automatically know that it's diagonalizable. So when you have repeated stuff, that's when it gets complicated. So you could say, following this statement, if you have all different eigenvalues, the matrix is diagonalizable. Okay, this is a statement that is true just based on like this little like comment above it. Very helpful in some cases. In other cases, not quite as much. But
If the matrix is if the eigenvalues if there are two eigenvalues that are the same, does that mean that the matrix is still diagonalizable or not? It's
it
not,
means it
right?
could be.
Yeah, you could have two eigenvalues that are same and diagonalize
You
it.
could have two eigenvalues that are the same and still have diagonalizable, but you could also not. So let's talk about this example question 13 someone pointed out. So question 13 on the practice midterm states A equals this matrix 1, 1, 1, all zeros on the bottom, 1, 0, 0. Okay, what are our eigenvalues of this? It is an upper triangular, so that from there we automatically know our eigenvalues, and they are the entries on the diagonal. So our eigenvalues are equal to 1 with multiplicity of 3. Okay. Eigenvalues have algebraic multiplicity. Eigenvectors have geometric multiplicity. Okay. Think of that like your eigenvalue is a number, it's algebra. Your eigenvector is a vector, it's in space, it has geometry. Okay. Algebraic multiplicity. It's just kind of implied when you write things like this. For when you have like a number with a multiplicity of 3, it's implied to be algebraic. All right, so now we find a minus lambda I, which in this case is just a minus I, right? Because lambda is equal to 1 3 times. So this gives us 0, 0, 0, 0, 0, 0, 1, 0, 0. Okay. Ignore the way I said that I wrote that. It's just kind of a roundabout way to do it. Anyway, how do we find our eigenvectors? Well, we find when this times some vector is equal to 0, which by definition is the null space. So let's find the null space of this. Once we put it in parametric form, we have x1, x2, x3 equals. So what two variables are free? If anybody wants to answer that.
So you have x1 and x3.
Precisely. And those vectors in this case are just 1, 0, 0 and 0, 0, 1. Okay, so this gives us our eigenvectors. Okay. The whole point of like doing this null space calculation is so that you can just pull your eigenvectors from it. You can kind of do this intuitively and say, hey, let's look at this matrix, and if I multiply it by 1, 0, 0, that gives me 0. If I multiply it by 0, 0, 1, that gives me 0. That's also a fantastic way to do it. This will never get you the wrong way though. This will never get you like a wrong answer. You can't like confuse too much of it. So this is like what is like easier to stick to, if that makes sense. So this you have a v1 equals 1, 0, 0, and you have a v2 equals 0, 0, 1. Okay. So how many eigenvalues do we have? We have 3, right? We have 1 with the multiplicity of 3. We have 1 distinct, but we have 3 total. That's what the whole multiplicity idea is. How many eigenvectors do we have? 2. Okay. So since they're not of like the same multiplicity, right? So here we have 2.
And correct me if I'm wrong, but can we also make eigenvectors out of linear combinations of these two?
Sure, absolutely. Because
Okay.
this null space here, right, it creates a plane. Here's x, y, and z. So it's going to make like this plane here. So as long as you pull 2 linearly independent things from it, totally okay. Okay, you could have like a 1, 0, 1 and like a 15, 0, 8. Totally okay as well. This is just like a very simple way to do it. But that is correct. So here we have a total algebraic multiplicity of 3. We have a total geometric multiplicity of 2, so it is not diagonalizable because we don't have 3 eigenvectors. Okay. Okay, questions on this?
Could
Is that from Britain?
it's not on this, but since could we go to question 14 since we're
Yeah.
right next to it?
Mhm.
I wasn't sure how to do this one.
Yeah, so let's talk about eigenvalues. So here we have question 14, and I'm just gonna okay. Oh. File, desktop, there it is. Okay. So here we have, hey, here's this one eigenspace and here's this 2 eigenspace. Find the value of k such that a times this combination of these two is equal to whatever. Okay, we're trying to find k. So algebraic or geometrically, how you can think about eigenvalues. This is one of the questions on one of the worksheets. So if we have we're in a plane and we have some line that we're reflecting over, okay. Say let's reflect over this, okay.
Zach,
Yes.
is there any chance you could please zoom in on question 14? Like zoom in on it because it's really small. Thank you.
Yeah, I'm just working to the side of it right now, and you guys can also, like, if you want to look at it in your browser as well, I'll zoom in on it as I'm like doing that part, but I'm just talking about like general eigenvalues right now. So like as we're reflecting over this, the whole like idea of an eigenvalue is that when we have a times an eigenvector, this gets us our respective eigenvalue times v1. So our eigenvector, when it's multiplied by a just acts as a number. It doesn't act as a matrix anymore. Well, it does, but it can be simplified into talking about it as just multiplying by a single number. So if we're reflecting over this line, there's 2 big like sets of vectors that are only changed by a single scalar, and those are those that are on the line because they're changed by a lambda equals 1, right? Nothing happens to them as you reflect it over. And those that are perpendicular to it, right? From here, this becomes a lambda equals -1, right? Because you're exactly flipping it over. And then what these 2 are, you can find these, just any vector on either of those lines. But that's what they are, like geometrically, is how you can think of them. So here, it gives us a 1 eigenspace and a 2 eigenspace. So let's go ahead and they give you your eigenvalues and eigenvectors, but this is just more geometric. So we have lambda 1 equals 1 because we have a 1 eigenspace. And we have lambda 2 equals 2 because we have a 2 eigenspace. That's what that means. Solid blue line. So let's pick a vector on here. I'm going to make it easy for myself. I'm going to say the vector is 4, 1, and the vector here, I'm going to say is 3, 2. Okay, these are just done by just picking them off of this. Okay, and another reason you might want to pick these is because they are right here. So, one of the parts about linear algebra, like the rules of matrix multiplication, is that it is distributive. So if we have a times a vector plus the second vector, this is the same thing as a vector 1 plus a vector 2. Okay, and we have a 4, 1 plus a 3, 2, right? So because these are eigenvectors, okay, we know a times that vector is just equal to lambda times that vector. So in this case, this is equal to lambda 1, which is 1, times the respective eigenvector of 4, 1, plus a times v2 is the same thing as lambda 2, which is 2, times v2, which is 3, 2. Okay.
Quick
Now
question.
Sorry?
Quick question.
Hmm?
If it was like, if it asked you to say like 20, if it was like a41 plus 32 is equal to 20k, would that be solvable or not really?
No, it would not be.
Okay. So in this case, it's basically like you can't multiply lambda by any number for this specific, like in this instance, because that would just not. Okay.
No. Yeah, this isn't like a great like general question, but like it's because they give you like, hey, this top one it ends up being equal to 10, and that is true. That's not like variable. That doesn't give you any new information. Okay, it's not like something to consider when solving the problem. It's more just like a check. Like they give you half the answer, you're finding the other half. And now for the bottom one, because this top entry is 4 times 1 plus 2 times 3, which is 4 plus 6, which is 10. For this bottom one, we have 1 times 1, which is 1, plus 2 times 2, which is 5. So in this case, it'd be C, k equals 5. Questions about this one? I see there's some questions in the chat. Hopefully people are answering them. How to find the volume of a parallelepiped and eigenvalues, eigenvector. So can you have repeat eigenvalues but not eigenvectors? Yes, I did believe I did answer that question. I can't remember if that was before or after that. But how to find the eigenvalues, I would do that in a moment. But first we have to talk about determinants. So what is a determinant? Long story short, it's a lot of things for a lot of different applications in math. And the main purpose we're using it for is we are finding like volumes and stuff like that. And we're finding like eigenvalues. Those are the big two purposes of our using of determinants right now. So volume of a parallelepiped is just the absolute value of the determinant of your three vectors. So if it says, hey, I have a shape composed of this, and these vectors. So they'd look like here's a vector, and here's a vector. It creates some kind of three-dimensional shape, right? So those pink lines are just me adding the other two vectors tip to tip from the others, the other ones that already exist. So this creates a nice little box, and how you do it is you find the determinant, the absolute value of the determinant of v1, v2, v3. Okay. And if they give you points, just find some vectors between your points. Make sure they're not the same vectors, but then from there, you calculate the determinant. Right? Because sometimes this will get you like a negative value, and you can't have a negative volume. So you just make it absolute.
How would you get vectors from points?
Yeah. So if I said, hey, we'll take it down to like a second dimension to make it a little bit easier for ourselves. So let's say we have coordinate plane. Say, hey, I have points 3, 0, 2, 1, and I don't know, 4, 1. Okay. So looking at this on a graph, which you don't have to do, this is 3, 0. We'll call this A, B, and C, just to name them on this plot. 2, 1 is B, and 4, 1 is C. So they construct this nice little triangle. All right. So when we do our vector algebra, one of the things to note is they create like a square or like a parallelogram, or that's why in 3 space it's called a parallelepiped, because it's most similar to a parallelogram in 2 space. So here, how to go between them, you just take like 0.1 minus 0.2. Okay, so 3, 0 minus 2, 1 is 1, negative 1. That is from B2A. This is our vector 1. Okay, that's this vector here. And then so basically you just pick 2 pairs of points and you subtract them. And then you pick a separate pair of points and you subtract them as well, and you'll get a second vector. So now if we do 4, 1 minus 2, 1, 2, 0. All right, so this is our V2. So now our matrix, it is 1, negative 1, 0, 2. Okay, and the determinant of this equals 1 times 2 minus 0 times negative 1. So obviously that goes away. So this determinant is equal to 2, but this isn't just this triangle. What it is it's this whole parallelogram. So you have to divide it by 2 when you're doing a triangle.
Quick question, Zach. Oh,
Yep.
whenever you're done, sorry.
Mm-hmm.
There's a question, I believe, in which it was given 3 vectors. Find the volume of the pyramid enclosed by these 3 vectors.
Mm-hmm.
How would you go about doing that? Would you do the whole like one? Would you take the determinant and divide it by 3?
Take the determinant and divide by 3. Where was that question?
It was on, I believe, like I was just like looking through, like I think it was in one. It was either in one of Margaret's notes or one of the practice midterms. From Jed Caskey's website, but I don't recall.
It depends on like how they're constructing it. But if it like cuts this in half, like this shape here, it would be divided by 2.
Wait, not 3?
Well, if it cut it in half, but from the pyramid you're talking about.
Like let's say it was given those 3 vectors. Find the volume of the pyramid.
Yeah. Let me think. I believe it'd be divided by 3, but that seems a little outside of anything that you guys have been doing, so I wouldn't worry about that one too much.
Okay. And I assume anything like with circles is also outside of the scope, correct?
Say that again?
Anything like if like we won't be asked like, given these 3 vectors, find the equation of the cylinder enclosed by these.
God, I hope not.
Okay. Well,
No, I don't think so.
Okay, cool.
I think that's a little outside of like the scope of this exam.
Got it.
So did you
The 2 and 0 were switched because I'm an idiot. That's why. I'm so sorry.
did you only need 2 like vectors instead of 3 because it was like a 2 by 2 or like a plane instead of like 3D space? Okay.
Yeah, exactly.
Okay.
So whatever space you're in, that's how many vectors you need.
Okay.
Okay, so this was in like a 2 space here. So we only needed 2 vectors to like fully enclose it. But in 3 space, you have like your 3 vectors, and then like you add them together, and you get this weird shape. So, but yeah, that's the idea. So whatever dimension you're in, that's how many vectors you need. I don't think they'll go very high for anything with volume. 4D volume is something that you should probably never use for a lot of different reasons. This actually still yields 0 minus negative 2, so that's still just 1 divided by 2. Could you have subtracted these vectors and gotten the same area? Yes, you could do any pairing of 2 points and you'll always find you'll get the same determinant. All right, so one of the let's talk about eigenvalues, eigenvectors, and characteristic polynomials now. Okay, so in this case, someone gives the vector or the matrix 3k to negative 1 such that k, I'm sorry, all lambda real, a is not diagonalizable. Okay, so one of the facts that we talked about is the volume of parallel. Yes, that is true, and note that other point. It has to be the opposite value of it. You can't have a negative volume. Such that lambda is real and a is not diagonalizable. So if a is not diagonalizable, that means that we have a lower geometric multiplicity, and what that means, then algebraic, and since we only have two eigenvalues, right, because it's a 2 by 2, for any like n by n matrix, you'll have n eigenvalues, period. Not necessarily n distinct, but you'll have n total. Okay, so remember this statement we were talking about earlier? Where'd it go? Here. Distinct eigenvalues give you distinct linearly independent eigenvectors. Okay, so in this case, since we're just talking about two things, if we had two distinct eigenvalues, this would be diagonalizable, right? So in this case, we know we have a repeated eigenvalue. Okay.
Question. And so even if we did have a repeated, because the goal here is, since it's a 2 by 2 matrix, we know that if there's a repeated eigenvalue, they won't produce linearly independent eigenvectors, correct?
That's what we're looking for, yes.
So only if it was a 3 by 3, it would be a lot more tricky, right?
You have to pay a little bit more attention to it.
Got it.
But regardless, what we're about to do is some fun algebra. So the characteristic polynomial, for whatever size matrix you have, okay, this is always true, okay, you have lambda to the n plus a whole bunch of garbage minus, I believe it's minus the trace of a. Somebody please correct me if I'm wrong. I always get that negative confused. Times lambda plus the determinant of a. Okay. This is true for all sizes of matrices, okay? Whatever's in front of lambda squared or lambda cubed or whatever doesn't tell us anything. But these last two entries tell us a lot of things, okay? Okay. Yeah, fantastic. So we have, in this case, we have a 2 by 2. So we have 2 minus trace of a, which is the sum of diagonal entries. Times lambda plus the determinant of a. Okay. All right. Is this from the makeup midterm or the practice midterm? Because this looks a little bit different than the one I think I remember doing. Let me check. Okay, well, we'll solve it anyway. Yes, from practice midterm, it is 6B. This is from Margaret's third midterm, fall 2020. Cool. All right, so what is the trace of this? What is the trace of this matrix? Okay, the trace is -3 plus -1. So no, +3 minus 1 equals 2. Okay. I guess I forgot to finish writing that down. My bad. So we have the trace is equal to 2, and let's solve for our determinant based on what we have already. So determinant equals -3 minus 2k. Cool. We're fine with this for right now. Okay, so we know our character's polynomial is lambda squared minus 2 lambda plus big parentheses minus 3 minus 2k. All right, so if you remember back to algebra or pre-calc or something, there is this fantastic method called completing the square. So what we know is we know that we're going to have a repeated eigenvalue. All right, so that means we're going to take the shape of some lambda minus some number squared, right? All right, well, let's write this as lambda minus c squared equals lambda squared minus 2c lambda plus c squared. All right. So this is just some algebra that you should be able to like put together. So you're getting this from knowing that your eigenvalue is repeated, right? So how do we do this? Well, we know that -2 from here is equal to -2c. This is a very complicated problem, by the way. This isn't just some like snap and you know the answer. But from here, you know that c equal to 1. All right. So if c is equal to 1, that means c squared is equal to -3 minus 2k. So 1 is equal to -3 minus 2k. 4 equals -2k. K equals -2. Right? So then you would put this back into this matrix, and you would see that you get a repeated eigenvalue. And then from here, you'd find the eigenvectors, and you'll find that you're only going to have one free variable. So let's 3, -2. Yeah, -2, -1. Okay, this is our complete A. All right. Now let's just walk through the exercise of finding the eigenvalues and eigenvectors for this, or the eigenvectors, because we know we have a repeated of 1, right? Because it satisfies this, and our character's a polynomial, and that's equal to 0. Okay. Does that make sense? Was that too fast? You could also put that equation into that form and solve for k as well. That's in the chat. That's saying that you can talk about the quadratic formula. B squared minus 4ac equals 0, because you're going to get a repeated root to the, a repeated root to the quadratic. All right, so here, a minus lambda I equals 2, -2, -2. That doesn't feel right. Oh, it's because it's a positive 2. That is absolutely why. Okay. So from here, you're going to row reduce it. Because remember, we're looking for our null space. Okay. So from here, we get it down to 2, -2, 0, 0. Or rather, just 1, -1, 0, 0. And from here, how many free variables do we have? We have one free variable. Which means we have one eigenvector. But we have 2 eigenvalues that correspond to this, so it's not diagonalizable. This is just like a check of that work. Okay. Can I explain 9b and 17?
How'd you know that there's only going to be one eigenvector?
So we know that there's only one eigenvector because right here we only have one free variable in our like null space calculation, because that's what we're like looking for here. So after we do a minus lambda I, we get this matrix, we row reduce it, and then we put it in like, well, this is just row echelon form, it's not row reduced, but regardless, we're getting it to be in this form, right? And there's one free variable here, so the null space is going to have one vector, okay? So you're going to find when you set it up in parametric form, I believe you'll get that. And that'll be your singular eigenvector. We can talk about Margaret's exam in a moment. So you can have one eigenvector corresponding to multiple of the same eigenvalues. Yes. You can have a bunch of you can have 2 with a multiplicity of 3 for an eigenvalue, and you can have less than 3 eigenvectors. You can have at most 3, and you have to have at least 1. But yeah, that's the idea right there. You have to have you can have at most the amount of eigenvectors as eigenvalues. Why this one I did is not diagonalizable. It is not diagonalizable because I have I have 2 eigenvalues, right? 1 multiplicity of 2, and we have 1 eigenvector. Okay, since these are not the same number, it is not diagonalizable. Okay, this number will always be equal to n and bigger. This number can be at most n. Okay. All right.
A quick question. Yes.
What was that?
How would you find the geometric multiplicity of the null space? I mean, of the eigenvector. Is it just literally the dimension of the null space? So it's literally the number of rows of the null space?
Not the number of rows. It's the number of free variables you have when you row reduce it.
Okay.
And from there, it's the number of vectors you have when constructing your null space. So here we only have 1 vector. So it's 1.
Okay. Got it. Thanks.
Mm-hmm. All right, I see questions for 9b, 17, and 6b. I will do those in order. 9b.
Wait, how would the number of eigenvalues be bigger than n?
What was that?
Can't you not? How would the number of eigenvalues be bigger than n?
Oh, it's not. Sorry, that is just an ambiguity in my writing.
Ah, okay.
Bigger.
Oh, bigger than the number of eigenvectors.
Yes. Yes.
Okay, thank you.
That is a good observation. You can never have more eigenvalues than you do columns.
Do the geometric multiplicities and the algebraic multiplicities have to be the same in order for something to be diagonalizable?
That is correct.
Okay.
Oh, yeah. For all of your eigenvalues. So if you have lambda equals 2 with the algebraic multiplicity of 3, and you have the eigenvectors with a geometric multiplicity of 3, so you have 3 eigenvectors there, then it's diagonalizable. Okay. All right, 9b. So in this case, it's a true or false question. So we have A is a 3 by 3, U equals 1, 1, 0, V equals 3, negative 1, 1. Eigenvectors corresponding to 4, lambda equals 2. Then U plus V is also an eigenvector of A corresponding to the eigenvalue lambda equals 2. All right, so come on. Yeah, for this one, God, why does I keep going to the top? This one is true, okay? So then U plus V also okay. This is a subspace question, but it is disguised as an eigenvalue eigenvector question. What this is asking is, given a space where U, V are both in it, does U plus V still exist within it? So we have a U equals 2U, a V equals 2V, and now we're asking, does a U plus V equal 2U plus V? right? Because this would be the definition if it was an eigenvector, right? A times the stuff, A times our vectors would just be a number times our vectors. Okay? So AU plus V, we can distribute AU plus AV, that's great, equals 2U plus 2V, because they're both eigenvectors corresponding to lambda equals 2, which is just equal to 2 of U plus V. Therefore, this is an eigenvector for lambda equals 2. That's just a quick check how you could do it. You could also just see that just this step here, and that would be true. Okay. Yeah, subspaces. All right, I believe the next question was 17. We'll do 6b. We'll get to 6b, yes. We'll do 17 next. All right, 17. So this is remembering some determinant rules. Okay. So determinant of A inverse equals 1 over the determinant of A. Determinant of A transpose is equal to the determinant A. And then you have to remember your row and your column operations. So of some number times A is equal to C to the number of rows times the determinant of A. A has to be squared to compute a determinant. That's just a fact. Okay. So these are some rules about it. Remember, one of the other things is if you multiply just a row, C, determinant is equal to C times the determinant of A. All right, so in this case, we have T of x, y, z equals kx, k squared y, k cubed z. And this is saying, suppose a three-dimensional solid S in R3 has volume 2021. Yeah, so this is talking about the transformation of S. So this T is being described as a matrix, okay? So this matrix A, what is it? So we're resulting in Kx, right? This over here, determinant of S equals 2021. That's what I just mentioned, but we'll get back to that fact in a second. Okay. So we have, this is our result. Okay, so let's make this A. How many x's are present? K, 0y, 0z. For the second entry, we have 0x plus k squared y plus 0z. And then for this bottom one, we have 0x plus 0y plus k cubed z. All right? So when it's asking to do the transformation of S, okay, what this is saying is this changes the determinant how, and this is our original determinant, okay? So this is just equal to the determinant of A times the determinant of S, okay? Which is k to the 6th, 2021. Questions on that? None. All right, cool. Now I'll move to 6b. 6b, which one of the statements is not correct? Is not correct.
Wait, how'd you get the determinant of A part? It's the k to the first, k to the second, and k to the third, so it'd be k to the sixth.
Correct. Yeah, good.
Okay, thank you.
Okay, so this one is which one of the following statements is not correct? Again, this is question 6b on the practice midterm. So I says an eigenvalue of A is a scalar lambda such that determinant of A minus lambda I equals 0. That is by definition true. That is what an eigenvalue does, because your goal is to have a free, at least a free variable, or in other terms, a null space. And to have a null space, you have to have a determinant of 0. So that A, for I, it is true. Again, this is 6b. So for I, an eigenvalue A is a scalar lambda such that A minus lambda I is not invertible. That is the same statement as the first one. And now we'll skip to IV. An eigenvalue of A is a scalar lambda such that AV equals lambda V for a non-zero vector V. Okay, so in this case, it is saying for a non-zero vector V, it is the corresponding eigenvector, because it's just some general thing. We can pick whatever we want. If it said for all, that would not be true. But in this case, this is just for a vector, so that vector is the eigenvector. That is true. That is the definition of this. An eigenvalue of A is a scalar lambda such that A minus lambda I times V equals 0 has a solution. This is missing one piece of has a solution. We read this very carefully. It's a scalar lambda such that has. Was that confused in the second? I'll get back to that in a moment.
Wait, you multiplied the k with their powers. You didn't add them, correct?
That is correct, yeah. Because we're taking the determinant and it's on like it's like a diagonal. So you just multiply them.
So what would it have looked like if like instead of k it was like a 5 and like it differed for the different so it
Yeah,
like
so it would be like 5k
7,
squared k cubed, so it'd be 5k to the fifth, and then it'd be k to the fifth times 5 times 2021 would be our determinant.
Where are you writing this? I couldn't see
I'm
that.
not writing this, I was just saying this.
Oh, okay.
Yeah,
Gotcha.
sorry.
Do you mind saying that one more time?
Yeah, so if it was like 5k squared k cubed, the determinant would be 5 times k squared times k cubed, which is 5k to the fifth. Okay, so I'll write this now. 5k to the fifth times 2021, and that's just k to the fifth times whatever that is. I'm not going to bother with the algebra because I don't want to accidentally mess it up. Now, eigenvalue A is a scalar lambda such that has a solution. This is very general. So this is for all V is what this is saying, because it doesn't specify, and that's not necessarily true. Because there is a null space, so you can think back to like column space stuff, so there's a place where we can't get. So 3 is not true. Okay. Because it has a null space, there is some V that there's not a solution. It's not very... They don't give you like a lot of information here, which you just kind of have to like say, oh, this means for all V, this means like all V can get back to the 0. That is not true for all V. All right, someone said they're confused on the second determinant rule. Determinant of A transpose equals determinant of A. So A transpose is just saying like, hey, if we have like 1, 1, 0, 3, the determinant of this is equal to the determinant of the transpose, which is determinant of just it reflected. Like you're peeling the bottom left corner and pulling it over itself. They write transpose in a lot of different ways. Some people just do an apostrophe. Okay. I'm not sure how it's standardized for this class, but characteristic polynomial. Yes, that is true. We use the characteristic polynomial to find eigenvalues. That is the whole point of the characteristic polynomial. Okay, so let's see. A question about a different simple midterm. Eigenvectors are closed under addition. That is correct. 6b on the sample midterm, we just did that. Your rotation scaling matrix always going to have complex eigenvalues. I don't know it off the top of my head, so I wouldn't go for like a genuine always kind of thing, but usually they'll give you the transformations and stuff, and then you can work it out.
Zach, may I ask a quick question that was earlier?
Mm-hmm.
So if two eigenvalues produce the same eigenvector, is the matrix diagonalizable?
That won't happen.
Okay, that will literally never happen. All right, cool, thank you.
Yeah, because that's that whole like law that we were talking about. Distinct eigenvalues mean linearly independent eigenvectors. Always, 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 always. Okay. Number 5. I don't have the different midterms pulled up, but if you could like type out the question, maybe I could answer it like that.
I could also share my screen if you wanted.
Could you maybe email me the file?
Yeah, I can do that.
Okay. Or just like a screenshot of like the individual question. Thank you. My email was at the top of the screen. It's ZRBRUMBACH. Also, if you type in Zachary Brumbach, it should pull up at Gautech. All right, so question 4 in the sample midterm. Question 4, suppose A is 3 by 3 with determinant of A is equal to 4. Find determinant of, let me write one more determinant rule. Determinant of A times B is equal to determinant of A times the determinant of B. Okay. So in this question, it asks A equals 4. Find -2. The determinant of -2 A inverse. Okay, so we know that the determinant of A inverse is 1 over the determinant of A. And we know that when we multiply something inside of this like equation here, it becomes that number to the power of the row. Okay, so in that case, this is a 3. So just your number of rows, because you're doing what you're doing when you multiply like 2 by like here, like we have the identity. Okay, what we're doing is we're multiplying -2 to each row. Okay, so that's why it's like we're doing -2 3 times here. So that's why it's -2 cubed. This is equal to -8 times 1 over 4, which is equal to -2. In what scenarios do you use transpose? Oh God. So this class focuses a lot more on like spaces and like how to find things, what they mean in terms of like the matrices themselves and like the space they're operating in. For like when you're actually doing like big matrix like algebra stuff, you'll have like orthonormal and you'll have like orthogonal matrices, which we haven't quite gotten to, and I don't know if we will get to. But the transpose is just an easier way of finding the inverse sometimes, and other times it's a valuable way to like transform a space. There's a lot of different like physical applications for it. All right, so are there any questions that I have missed? Let me check my email. Cool, there's that question. Insert, file, nope, come on, there's. Okay. Is there any particular part of this that you would like to go over? I see a second question from, well, where'd it go? I got where my email go. There it is. Fantastic. So was there a particular, I saw yours as well, Anna. I will get to that in a moment. So is there any one of these 4 that you wanted to go over for the person who sent me this?
The second one and the third one, but mostly the second one.
Mostly the second one. Okay. Okay.
So can you also go over the first one as well?
I'll just do all of them, yeah. Okay, So every non-zero vector in R2 is an eigenvector of A. So that is a little confusing, but you can think of it as you have two different eigenvectors, right? And they compose all two space. So all of your like vectors you're given, whatever they are, can be composed of these two things. Okay, you can break it down into some linear combination plus v1, v2. Okay, for all v1, v2, for all like b vectors that you're like solving for, like this vector being like any vector in A. Okay, and v1 and v2 are your eigenvectors. This has a solution, right? Why did I write that? Has a solution. Okay. So since all vectors can be deconstructed into those, yes.
Okay, I think I kind of understand that.
Huh?
Said I understand what you're saying. So that means every single non-zero vector in R2 is an eigenvector then.
It can be deconstructed into eigenvectors, yeah. Which I
Okay.
believe means the same thing in terms of how they define it. Okay, so that's repeated multiplication by A pushes vectors towards span of 2, 3. Okay, so what this is saying, repeated multiplication by A is A to some really big power. Okay, A to some really big power is 1, negative 1, 2, 3, negative 1/3, 1. Okay, and here, I believe it's switch. It's switch A and D, correct? 3, 1, negative 2, 1. Or the inverse of a 2 by 2. Nope.
It's supposed to be negative signs? Okay.
Yeah, my bad. Not inverse. Yeah. That's the definition of your inverse for a 2 by 2. What can I write? Okay. So here, as A goes really big, these values get, like this matrix is the only one that's raised. Because essentially how you can think about it is we have like some eigenvector, like in space we have some eigenvector, and say every time we multiply by A, it gets multiplied by negative 1, okay? So as A gets really big, we just multiply it by whatever that power is. Okay, so that might not make a lot of sense immediately, but we're going to work this out, and then you're going to see it algebraically as well. The key says that only 2, 3, and 4 apply. Oh, okay. So it's not an eigenvector, but it can be constructed of eigenvectors. Okay, so it's just a difference in definition. They're not going to ask you a question like this, I don't think. If it looks totally foreign than anything you've seen before, you can probably expect that you won't see anything like it.
Was this even on the practice midterm at all?
This is on a different practice midterm.
Oh, okay.
Like one of the ones from like Margaret's past years, I believe. So not every eigenvector is, but every eigenvector can be deconstructed into. Okay. Repeated multiplication by A pushes vectors towards the span. All right, so for a diagonal matrix, when we raise it to a really big power, we'll call this power n. Well, we'll call it, I don't know, C. Okay, raised to some power C. All right. For a diagonal matrix, what happens as you multiply it by itself is just the entries on the diagonal get raised to that power. All right, so now we do some matrix multiplication like this. We're going to have times 1 times negative 1. We're going to have 2 times 1 to the C, 3 times 1 to the C. times 3, 1, negative 2, 1. Okay. So this is equal to push to the span of 2, 3. Okay, so before we go any further, what is, as we raise like 1/3 to a really, really, really big power, what happens?
It goes to 0.
It goes to 0. Yeah, so we can just say this goes to 0. Okay. I believe the answer key had AI was false. I believe that's what the answer key said. Someone said that.
2 would be true. Like 2, 3, and 4 on here is that the answer key said that those answers were the
Okay.
ones in the circle.
Gotcha. Cool. Yeah. So then that's how. Yeah. So if it's not an eigenvector, all things are constructed of eigenvectors, but they are not eigenvectors in this case. So it is false. That for I. Okay. So for this next one, we have. So we can agree that, well, so we're going to do this matrix multiplication. We get 0 plus 2 times 1 to the c. 0 plus 3 times 1 to the c. And over here, 0 plus times 1 to the c. And 0 plus 3 times 1 to the c. Okay, so this, when you have 1 to the c, it's just 1, right? So this gives you 2, 3, 2, 3. Okay, and what is the span of this?
2, 3.
2, 3. I believe, yeah.
This seems like too many steps for like one question.
It does feel like a lot. Essentially what you can like see right off the bat is this first one is a fraction, so as it gets really big, it's going to go to 0. So the only vector you're going to have left is the other vector.
So wait, I'm a little bit confused where you're getting this other vector from exactly.
The 2, 3?
No, the rest of it, the AC part. Did they give that to you?
Oh, it's just saying like repeated multiplication by a. That's a raised to the c. Because we're multiplying a by itself that many times, which is repeated multiplication, which is just a power.
Oh, so the answer is because it goes really small. The only thing that really remains is the 2, 3. That's it.
Correct.
Okay.
Question 3 is extremely similar. If a equals negative 1, 1, then an of x approaches the 0 vector as n becomes really large. Okay. What do you notice about this vector? It is almost identical to this by a scalar, right? So it exists on that same span, so it is still like considered an eigenvector, right? So like we just talked about here, this vector, as this gets really big, because that's the corresponding eigenvalue to eigenvector, as this gets big, it goes to 0. Therefore, this must be true. That's the same thing that I just said. This is just in like a statement. If x equals this, then a to the n of x approaches the 0 vector as n becomes very large. Yes, it does. Because negative 1 over 3e raised to a really big power is equivalent to 0. Questions on that? And then for 4, that one should be pretty straightforward. Eigenvalues of a, boom, boom, done. Pull it right off the diagonal in the middle.
Can you re-explain 3? I'm very confused about how to do that.
Yeah, so this is what I was talking about with like 2 and 3. like this whole work I did for 2 is the same thing about 3, okay? So we're showing as a of n goes really, really big, okay? Because a of n of -1, 1, okay? The same thing as -1, a of n, 1, -1, right? We're just taking that negative out of here. Well, I guess we can keep it on the right side, but times -1, okay? So now this is our eigenvector, right? And every time we multiply our eigenvector by a, we multiply by the corresponding eigenvalue of -1/3. So every time we multiply this vector by a, it becomes smaller, right? So as it keeps
Oh,
getting smaller,
okay.
it goes to 0.
Okay.
Cool. Questions on this? Cool. Insert file. No, that's the same picture. Damn it. Suppose A is 2 by 2, his determinant is 1/2, and his cofactor matrix is this. We haven't really talked about anything in terms of cofactor matrices, I don't think. I believe that's just an outdated term from a different semester. Anna, do you mind? Anna, I'm not sure which one it is. Anna, could you tell me what semester and exam this is from?
Yeah, this is from, let me get it up. Margaret's, yeah,
And is it Anna or Anna?
it's
I think that
Anna.
was. I think it's last year's exam,
Yeah,
if I remember.
yeah, it is. It's fall 2020.
Okay. And how do they define cofactor matrices for you? Is that the A minus lambda I?
So the solution
Mhm.
it was like A inverse equals 1 over the determinant of A and then times C of T, like C, like transpose, I think. I can also send a picture of the solution
Okay. If you
if you
could,
want.
that'd be great.
Okay, yeah, I'll do that. I was just a little confused by it, so.
Okay. Yeah, yeah. We haven't used the term cofactor matrix, but we'll talk about it really quickly about what that means in terms of this class. Because one
Is
of the things you
cofactor
guys learn
matrix
is what?
doesn't mean the inverse matrix without doing the 1 over the determinant?
Without doing 1 over the determinant.
No, is the cofactor matrix just like D? Is it D negative B negative C A?
Off the top of my head, I cannot tell you the exact definition of a cofactor matrix because one of the things you learn
Okay.
as you take more math classes at Tech is in every class they define things a little bit different, which is extremely annoying. There'll be some things like eigenvalues, eigenvectors, which will be the same.
Wait,
Um,
quick.
yeah,
So, so if I add two eigenvectors, do I get, if I add two eigenvectors, because it said earlier, in your earlier question it was false. In the
yeah,
earlier,
the one I just did
yeah, why was it false?
because they're not the exact like given eigenvectors.
Oh, because it can be any.
Yeah, in this case they're set, like they're set to be these two. But
But
any vector is constructed of those two. They're linear combinations of them.
then why is one not true?
It has to be. I think it has to be the same eigenvectors to add them. Sorry,
In this
eigenvalues to
case,
add them,
yeah.
right?
Yeah.
Oh,
It's just like a semantic thing, right? Because it could be a different statement. Say, hey, if we have two repeated eigenvalues and we have two, because like in this case we have two distinct eigenvalues which give us two linearly independent eigenvectors. They're not subject to change, right?
oh, I see. But if the thing on the bottom right was like a minus 1/3, then number one would be true.
Yes.
Okay,
Yeah.
got it.
Cofactor matrix we can compute. Okay, yeah, this is a definition for a term that you guys haven't used. This is the definition of a cofactor of
So we're not responsible for this type of question, I'm guessing.
I wouldn't say so, but I'm still going to write the formula for it. It's A inverse equals 1 over determinant of A, okay, times cofactor matrix transpose. That's the definition of it. If you haven't seen it in your
We're gonna
class, if
need
you
to
haven't
know
seen it
this.
in your notes, you can expect it not to be on the exam.
Okay.
That's a fair assumption for just about all classes. And that certainly holds for here, I hope. Somebody asked for question 18 on exam midterm. So, question 18. Oh, good Lord. All right, so this is a large jumbled mess of numbers and stuff, but we can break this down pretty quickly. One of the hardest things about these questions is trying to digest some of the stuff they say. Because sometimes it feels like a lot more than it is. And in this case, you have a lot of different numbers and a lot of different things going on, but you can actually move through this one pretty decently fast. Well, not fast, but just like it's very straightforward. So in this case, we have a 2 eigenspace, and we have a null space, okay? And a null space is a lambda equals 0 eigenspace, okay? Because remember, our a minus lambda I has a determinant of 0. And if A's determinant equals 0, that means lambda equals 0 must... Oh my god, why can I not write? Another fact to note is the determinant of any matrix is equal to the product of eigenvalues. The same way that the trace is equal to the sum of your eigenvalues. Okay, just 2 things to note. So in this case, we have a lambda equals 0, and we have a lambda equals 2. And another way you could think about this is the determinant is 0. So the determinant is your product of all of our eigenvalues. So 0 must be included if determinant is 0, right? So this is a CDC inverse. So just like looking at the format for A, we can cross this one out because the middle one is not diagonal. And we can cross D out for the same reason, okay? And we know we have lambda equals 2 and lambda equals 0, so anything that doesn't have 2 and 0 on the diagonal, so the rest of them are good. No. Okay, they satisfy that condition. All right, and what are our eigenvectors? So this says it's the line of this. So let's pick some numbers. So let's find a vector that satisfies this, is what that means, okay? And this vector would be 1, 3. So I'll just plug in 1 here, and then I'll find that my x2 is going to have to be 3. And that's how you determine that vector, okay? So for the second one, x2 equals negative x1. Let's set x1 to be 1. And what does that mean my vector is? It means it's -1, -1, right? Because if I plug in 1 here, if x2 equals -1, right? These are our 2 eigenvectors. All right, so let's go down this list now. Because remember that we have to have v1, v2 corresponding to lambda 1, lambda 2, right? And then C inverse over there. So for B, does the vector 1, 3 correspond to the eigenvalue of 2? Yes, it does. Does the eigenvalue of 0 have the eigenvector -1, 1? Yes, it does, because it is a scalar of what we have, okay? So we could also pick, instead if I picked like x1 to be -1, I'll find that x2 is 1, okay? Exact same idea. And then just double check, yeah, But let's go through the rest of them anyway. So does this eigenvector correspond to this eigenvalue? No, it does not. Okay, that one's out. 1, 3 does not correspond to 0. That's why that one is eliminated. Does the eigenvector 2, 3 correspond to our eigenvalue of 0? It does not. Another way you can check is to plug them back into your equations that are given. Does the eigenvector eigenvector is 2 Earth? Yeah, B is the answer. It's 3, 1. My stupid head. Okay. Does this correspond to this? Yes, it does. Does this eigenvector correspond to this eigenvalue? No, it does not. It is backwards. Right? So that's gone. Does this vector correspond to this value? No, it does not. Therefore, B is our answer.
I have a question.
Yes.
So could you also have picked a value for x2 when you were finding your vectors instead of x1?
Absolutely.
Okay. And then is the null space always lambda equals 0?
Yes.
Okay, thank you.
The null space always corresponds to that, yeah. All right, do you guys have any more questions? About anything at all? It doesn't have to be like a certain question. Like, it's okay. You can have like a, hey, I don't understand what like a trace is or anything like that. Any questions at all?
Can you explain why this one isn't E again, or I mean F again, so fast?
Yeah, it's not F because I thought it was F for a second because I am dyslexic. Because this vector here is not the same as this vector here. That is 3, 1, which is not the same as 1, 3.
Can't you for calculating the eigenvector, they said this shortcut for like complex eigenvectors that we could use for everything was like negative y over x. Does that always work?
It does.
Okay.
Yeah.
So like
for
for this one,
complex,
since it was like x, what was it? X2 equals 3x1. Could you just do -1? Wouldn't it be negative then, or no? Like how would that apply to x2 equals 3x1?
it's if they're on the same side.
Okay, thank you.
Okay. Yeah, and for complex eigenvalues, they always come in pairs. And when you take your a minus lambda I, or lambda 1, okay, you're going to get some, or like a 2 by 2. You're going to get something with some 2 values, and your eigenvector is equal to negative BA. Okay? And for its conjugate pair, so if like this is equal to like 3i, this is negative 3i. If it's 2 plus 3i, it's 2 minus 3i down here, okay? V2 is equal to complex conjugate of that. Okay, that's what this big star means, complex conjugate. So whatever it is, like if you have like an I1 for V1, that means V2 is negative I1. Okay. All right. Any more questions?
Could we do in AX equals B problem, like solving for X with like B times A inverse, I think is how you're supposed to do it.
So written like this or written like how?
Yeah, I think it's usually a small b.
like
Yeah.
this. Okay. Yeah, so the whole like reason that we can do eigenvalues and eigenvectors is that the matrix is square, right? And when we're talking about determinants, to have a non-zero determinant means that it is 1 to 1 and on 2, okay? Which is the same thing as saying it's invertible. Okay? If it's 1 to 1 and onto, basically what that means, when we take AX, there's a way to get back from our B. Okay? And the way to get back is multiplying B by A inverse. Okay? So I'm not sure what you mean by that question about these. Like, do you have like a numeric something that you're looking at, or like?
No, it was just one of the questions that I had trouble on when I was doing like a practice past
Okay.
one involved AX equals B, and so I was just, I guess, making sure. So with that one, if you're given like a B vector and A, so you would just find the inverse of A, multiply it by the B vector, and then that would
Yeah.
be X.
So an
Okay.
example of like I think the question that you saw would be like, find X such that AX equals 2, 3, 4. A equals 1, 4, 0, 3. Okay, like something that looks like this.
Yeah.
Okay. So this is our B, right? Okay, and this is our A. So what we do with matrix multiplication is we can left multiply by A inverse. So we get A inverse times A times X equals A inverse times B. Okay, see how we just did it to both sides? And now A and A inverse multiply to be the identity. And now we have X equals A inverse B. And that is 1, 0, 4, 3 inverse times 2, 3, which is equal to 3, 1, 0, negative 4 times 2, 3 is 6 minus 12, negative 6, 0, 3, 3. Okay. So this is equal to your X. And what you'll find is you can check it by plugging it in for A times X. So when you have 1, 4, 0, 3 times negative 6, 3, you're going to see that you're going to get the same 2, 3, I believe. You should. I think I calculated this a little wrong, but that's okay. Whatever, but this is how you would do it. Okay.
When finding the inverse, do you multiply once you swap and make them negative, do you multiply by the determinant?
Yep, that's exactly what it was that I forgot to do.
1 over the
Isn't
determinant?
it 1 over the determinant? Yeah.
Yeah, my bad. I always forget that step. Sorry. What's that, 1/3? Yeah. Okay. There it is. Okay. And now you'll find that you'll get 2, 3. Okay. Did I already go over question 13 on the sample midterm? Let me check. I went over question 13A, and we talked about how it's not diagonalizable. But for 13B, I'm just going to talk about it instead of writing it down. The 2 by 2, actually, I'll write it down really quickly. So what this is talking about is like, here's the line we're reflecting across. 5x equals y. So something that looks like this, okay? So this is the line we're reflecting. Base. Okay, the coordinate plane. Okay. What are our eigenvalues? Well, if something sits on this line, it's changed by lambda equals 1. And if it sits on a perpendicular line, it is changed by lambda equals -1 because it's just flipped over. So how many distinct? How many distinct eigenvalues do we have? 2. Therefore, we have 2 linearly independent eigenvectors. Okay, and since we have 2 eigenvectors and 2 eigenvalues, then it is diagonalizable. All right, and a question in the chat says, suppose A is n by n, and lambda is an eigenvalue. If V and omega are 2 different eigenvalues at the corresponding, I think that's supposed to say if V and W are 2 different eigenvectors of A corresponding to eigenvalue lambda 1, then V minus W is an eigenvector of A. Can I explain why this statement is true? Yeah. So V comma W eigenvectors. My apologies for my shitty writing. For we'll call it lambda 1. Okay. So remember the definition of an eigenvector is A times that vector is equal to lambda times that vector. Okay. So in this case, X is E minus W. Okay. And one of the laws of matrices is that we can distribute. Is that supposed to be V minus W, or is that supposed to be V plus W?
V minus W.
Okay, cool. So this is equal to lambda 1 V minus lambda 2 that. Okay. This is confusing. But now, sorry, not confusing. V1 minus W, not V1, just V. Okay. Which is what we were checking, right? So it yields the same since A times this is the same thing as just lambda times that. It is an eigenvector as well. Okay.
Which question is this?
I don't know. It was typed in the chat. I think this is just a general question, which is fair.
Wouldn't you need to keep lambda 2 also?
Oh, that's
wait,
lambda
no,
1.
'cause
They correspond to the same lambda. That's my bad.
Ah, okay, gotcha.
All right, you guys have any more questions?
Can you also explain what a transpose is?
Yes. So A transpose. So what it is basically like you have your matrix. Okay. And the transpose is basically like if you have this like line here and you like pinch this corner and drag it to the other side. Okay. That's how you can think about it like written. Okay. I know that probably sounds confusing, but it's a lot easier than you might think it is. So you're basically switching your rows and columns. Okay. Okay. So what you're doing, like this is reflecting over, reflecting over, reflecting over, reflecting over. Like literally like you just grabbed the bottom corner and dragged it over. Okay. In terms of like the applications of that, it can mean a lot of different things. Not a lot computationally right now. Okay. Does that make sense? I know it's not a great answer, but
Yep, that makes sense. Thank you.
okay. Yep. So any vector that is a linear combination of eigenvectors is also an eigenvector. I believe that's so long as they correspond to the same eigenvalue, okay? So like one example would be like for the question we were talking about earlier, like say we have v1 for lambda 1 and v2 for lambda 2, okay? Let's go back. Almost there. Here. Okay. So for this here. Okay. Nope. 3 lambda 2 equals 1. Okay. So let's say I give you the vector, I don't know, 3, 2. Okay. 3, 2 is a linear combination of these two eigenvectors, okay, added together. So 1, negative 1 plus 2, 3. Okay. So what happens if I multiply it by a? All right. So from here, we get a 1, negative 1 plus a 2, 3. This is for distinct eigenvalues, right? Because we have two totally different ones here. Okay. So this gives us negative 1/3, 1, negative 1 plus 1, 2, 3. So what this is saying is like any vector can be composed and broken down into a form like this, but the amount that it's like present is different, right? Because in this case we have like this one times 1, this one times 1, okay? If I gave you 5, 5, right? This first one times 1, and the second one times 2, okay? Okay. So it's clear that you can't just like pull out the same eigenvectors, but they're still like, they can still be broken down and used appropriately, if that makes sense. So that's why like here, all vectors can be broken down into components that are eigenvectors, but they are not all eigenvectors. Because it's not like a simple scalar, like in this case, right? Like we have 1/3 plus 2 times a different part of it. Sorry I didn't explain that part a little bit earlier. But any last questions?
Wait, can you explain that one more time? I got kind of confused. Can you switch the eigenvector to be 2 from being negative 1/3?
Oh, no. The eigenvectors are still out here, right? Okay. I'm just multiplying, like, I'm breaking up, like, this vector is...
So would you multiply by the 1 first and then you can multiply by the 2?
Yes.
Okay.
That's 6. Does that make sense? Yeah. I did a not great job of explaining that the first time, and that is my fault. But hopefully it makes more sense to you now. Any last questions before we go?
This is just kind of a general question, but do you know a good way of like memorizing kind of the different like synonyms for everything?
It's hard. That is a fantastic question. It really just like comes with just doing it over and over, like the repetition of it. That's what like the homework is made to like nail into your brain. Like just a few definitions that you should like know. Whenever you see something equals 0, null space. Okay, that's what you're finding. All right. Whenever you're asked like if the determinant is 0, that's like your determinant is 0, you have a null space, there are free variables. There's not like an easy just like set of words to just remember it, unfortunately. I would just refer to like sometimes in like the PowerPoints for class you have like your list of like, hey, all of these things are equivalent. Like when we got to like column space and null space, looking over those, and then onto and one-to-one as well, looking over those may be worth your while. Just to
Okay.
like see what definitions all mean exactly the same thing.
Okay, so like the invertible matrix theorem, like
Mhm.
all of those, would that be a good way to kind of just go through and do that?
Yeah, just
Okay.
if there's a list that says, hey, all of these things mean the same thing, just like maybe calculate it one way, like, hey, for this one, like find the determinant, and if it's non-zero, it's invertible. And the next one says, if it is onto and one-to-one, it's invertible. If the columns are linearly independent, it's invertible. Like, see what each of those means numerically, and you'll actually come to the conclusion that they all mean the same thing.
Okay. Thank you.
Absolutely. All right. We're a little over time, but that is absolutely okay. You guys have a great night, and good luck on your midterm tomorrow.
Thank you.
Figure
Yep.
out